Mathilde Gerbelli-Gauthier on cohomological representations. And well, I guess we're on Zoom now, but she's from McGill, and let's hear the talk. This should be fun.
Thank you. Thank you, Rahul, for the intro. Thank you to the organizers for inviting me, to Bhaskaracharya Pratistan and Isra Pune for hosting this wonderful year of talks on the work of Harish-Chandra. As someone who works on automorphic representations and sort of specifically on certain local aspects of automorphic representations, I feel like all of my work sort of downstream from the work of Harish-Chandra. So it's a great honor to be able to speak in this series of lectures. So this is part of a series of talks in the third trimester in which we sort of look at certain topics where the work of Harish-Chandra has had an influence. And in this case, we're going to look at the cohomology of arithmetic groups. And specifically, we're going to look at sort of the spectral analysis of the cohomology of arithmetic groups, so how it has to do with representations. And so these two talks that I'll be giving this week are on cohomological representations, so sort of the representation theoretic input to the cohomology of arithmetic groups. And so, let me get started. Then we can see. Okay, so first, I'll start with motivation and some recap from last week's talks. So the setup in general, so I'll start with a sort of general global setup for what we want to be thinking about, and pretty quickly we'll move to sort of more Archimedean local considerations. So F will be a number field with completions FV, AF will be its adels, and sort of if I put an infinity or any subscript above, it means away from, so AF will be the adels away from infinity. G over F will be a reductive group. Today, the only examples that we'll see will be SL2, but on Thursday, I'll sort of talk a bit about SP4. That's not true. I think I say something about some reductive groups a bit later. K infinity will be a compact open subgroup, so a compact open subgroup of the finite adels. And then we'll be interested in a lattice gamma, which is the intersection of the rational points with this compact open subgroup. So now this is an arithmetic group in the Lie group that I get by taking the infinite points of G. And then as a last piece of data, I'm going to be taking the cohomology of gamma with values in a certain coefficient system. And the coefficient system will be a finite dimensional representation E of this group G of F infinity or G infinity. I should say I welcome questions at any moment in the talk, and I welcome interruptions. And if I see any sort of alert that someone is asking a question in the chat, I'll answer it. But if I don't see it, feel free to unmute yourself and ask. Okay. So in this series of talk, as I was saying, we'll be interested in the cohomology of the lattice gamma with values in E and in some of its variants, which I'll explain a little as the talk goes on. So what is this cohomology? Well, one way to view it is that really it's the group cohomology of this discrete finitely generated group gamma with coefficients in E, so it's the derived functor of fixed points. Another way to see it is that under mild assumptions, we can take a slightly more topological geometric perspective. Okay, the mild assumptions will be on gamma, and it's sort of nice enough for it to be the fundamental group of a quotient x gamma that I get by taking sort of this discrete action of gamma on a certain symmetric space x. So x is the symmetric space associated to G infinity, take a quotient by gamma, and then the coefficient system becomes sort of from the action of gamma a local system on x, and then I'm looking at the cohomology of x gamma with values in this local system. So what is X? As I said, it's the symmetric space associated to G. It depends on G, in particular on G infinity. And it'll be a manifold, a real manifold of dimension of G infinity minus dimension of K infinity. So K infinity would be the maximal compact subgroup in G infinity. For example, G infinity was SL2R, in that case, X is the hyperbolic plane. It's a real surface. If G infinity was SL2C, then X is hyperbolic 3 space. And in the example that we'll think about the most on Thursday, if G is the symplectic group, the 2 by SP4R, then X will be the six real dimensional Siegel upper half space. So in any case, I can sort of imagine that my cohomology is a cohomology of a finite volume space X gamma obtained as a quotient of one of these symmetric spaces. Okay, and so where does representation theory come in? Well, it comes in because I can relate, and we saw this in Ankit's talk last week. I can relate this cohomology, I can sort of decompose it in terms of representations of G infinity. So I'm going to start with the assumption that gamma is co-compact. So that means that this quotient that I get will be a compact manifold. In that case, I can consider the space L2 of X gamma, so L2 functions on this compact manifold. It carries an action of G, and it decomposes as a Hilbert space direct sum of irreducible representations pi with possible multiplicity, so with this finite multiplicity m gamma of pi. And the beautiful sort of thing about cohomology, the sort of what we get from Matsushima's formula, again, what was explained last week, was that I can sort of leverage this decomposition into a decomposition of the cohomology. So there's a decomposition of the cohomology where it decomposes where I can write it as the cohomology, so that the so-called GK cohomology of each of these representations. So let me just read it. HI of gamma with coefficients in E decomposes as a direct sum over the unitary dual of pi of the multiplicity of pi at level gamma, and then the cohomology, the GK cohomology of pi tensor to E. And of course, the thing on the left is finite dimensional. So the thing on the right better be finite dimensional, and many representations won't have cohomology. So this HI, GK infinity pi will be 0. And we'll talk today about the ones for which it's not 0. Okay, so this Matsushima's formula, which we saw last week, it reduces the computation of dimensions of cohomology to really computing these multiplicities m gamma of pi, which of course is no small feat, and to computing the GK cohomology of the representations pi. And I'll really focus in this talk on the right side, so on the second step. So what is the GK cohomology of these representations? Okay, so a recap from last week, just the highlights on GK cohomology. Okay, I'm going to switch notation now. G is no longer my global group. It's going to be the Lie group G infinity, because all the action from now on is just going to take place at infinity. So really, it'll be a real group. Okay, so to each irreducible unitary representation pi h, first we can pass from the representation to the Harish-Chandra module of smooth k finite vectors in the representation. And I'm going to abuse notation throughout this talk. I'm not, when I talk about the GK cohomology of something, I'm not going to be it's not always going to be clear if, like, sometimes as the coefficients I'll put a unitary representation, and I mean really the underlying GK module, and I'll be sort of not attentive to whether as a coefficient system I'm thinking of the unitary representation or the underlying GK module. Okay, and so given a Cartan decomposition of the Lie algebra of G, sort of separates the Lie algebra of G into the Lie algebra of the compact subgroup, and then this P, which is really the tangent space at the identity of the symmetric space. GK cohomology we saw last week, is computed from this complex where the Qth part, the Q chains, if you will, are the k-homs from the Qth exterior power of P to my representation V. with a complicated differential, which was written down in the talk last week, and which I'll write down. It'll appear a few slides from now, but I don't want to write it down just now. So for now, for this talk, we'll think of GK cohomology as really the cohomology of this complex. Okay, so that was just a recap on GK cohomology. Now I want to say a few words. It won't really matter for the rest of the talk, but I just want to say a few words about what happens if gamma is not compact. So I can take the space of smooth functions on G mod gamma, which is no longer a compact space. And last talk, we saw that, okay, before we go to sort of the decomposition of L2, we can see that in general, the cohomology of gamma with coefficients in E is equal to the GK cohomology of this giant, valued in this giant representation, sort of the smooth vectors, the smooth functions on G mod gamma tensored with E. The problem is that, okay, so when gamma was co-compact, then these smooth vectors were dense in L2. In fact, they were the smooth vectors in L2, and so you can sort of relate this space of C infinity G mod gamma to L2 G mod gamma, and then work with unitary representations. If gamma is not co-compact, this C infinity of G mod gamma, it's too big to work with. Sort of in practice, it doesn't buy you much in terms of computations. In particular, it's not semi-simple as a representation of G, or it's not even the completion of something semi-simple as a representation of G. So one fix is to only deal with the part that you can work with. So, I mean, I think a theme in harmonic analysis on all the talks this year has been that if you have functions on a group, or here functions on quotients of a group, you can sort of decompose the L2 functions into the discrete part, so sort of the completion of the direct sum of the irreducible representations, and the continuous part, which is whatever is left. So one fix is to do this, to decompose L2 G mod gamma into these two bits, and in the left-hand side, inside of the discrete part, then I have a dense space. Well, the discrete part I should have written, sorry, decomposes as a direct sum of unitary representations, with the Hilbert space completion of a direct sum of unitary representations. And so I can study it as if the group was co-compact. And so in this case, I put a decoration on my cohomology groups, which is that instead of studying the ith cohomology, just sort of regular group cohomology, I'm going to study the L2 cohomology. And all that is, as I said, is just the discrete part. And so in there, I can find a space of smooth functions, find Harish-Chandra modules, et cetera, and then compute GK cohomology. Okay, so I just want to sort of give you a sense of what can be done. This H2i, in some degrees, it's equal to the whole HI, but in general, it's smaller. But it's a piece that of the cohomology that we can access with these spectral methods. Okay, so moving back to representations. So I'll call a representation pi h cohomological if there's a finite dimensional coefficient system such that the cohomology doesn't vanish. The goal of the talk, now that I'm done with its intro, is to characterize cohomological representations, or sort of to tell you what cohomological representations look like. Okay, to give an outline of their construction, mostly I'm going to give a parametrization of them. I won't really be very precise about the construction. And mostly just to convince you that they're very well understood objects, 50 years almost. Several decades, we've known what they're like, what they are, and they've been characterized. We understand them very well. When you see cohomological representation, you just think, okay, it's one thing in this finite list of things that are very well understood. The next talk, so today will be a little thin on examples. As I said, I'll talk about SL2 a little bit. But in the next talk, I intend on completely describing all the representations with trivial coefficients in the case where G is SP4. And so really give you a concrete sense of what these cohomological representations are in the case of SP4. And the reason I chose SP4 is because I think we're working towards some talks by Kartik Prasanna. Well, he'll talk about some work on the derived Hecke action on cohomology anyways, and this paper that we're working towards is for SP4, so that's what I'll talk about SP4. sort of to get us ready also. Okay, so that was the first part of the talk. I'm going to have a sip of water. If someone has a question, you can ask a question. Otherwise, I'll move on. Okay. So characterization of cohomological representation. So let's remember, what is a GK module? Well, it's a compatible representation of either the Lie algebra G or the universal enveloping algebra of Lie algebra, whatever you prefer, whatever framework you prefer, and of K. And we saw last week all the compatibilities, the sort of several necessary compatibilities and conditions that have to be satisfied between the action of G and the action of K. In particular, the restriction to K is going to be semi-simple, and we'll be interested in a particular class of GK modules, the admissible ones, in which each K type appears with finite multiplicity. And the most important example that we'll keep in mind is exactly the representations we're studying. If pi is the smooth K finite vectors in an irreducible unitary representation, then pi is admissible. And so the upshot of this is, we'll often think of pi, like if you want to have a picture of pi in your head, you can think of it as a string of K types, just sort of a direct, just think of its restriction to K. And that already tells you a lot of information about the representation. So it'll just be sort of a direct sum of infinitely many, typically, finite dimensional representations of K. And if you know that, you already know a lot about the representation. And to talk about cohomological representations, we'll introduce a second invariant, which comes from the action of the center of the universal enveloping algebra. So in the center of the universal enveloping algebra, it's sort of looks like the violin invariance in a polynomial algebra, but anyways, it contains one special element, which I didn't write in coordinates, but I think was written in coordinates last week, called the Casimir element. And since C is in the center of the universal enveloping algebra, there's a version of Schur's lemma that says that if pi is irreducible, then pi of C is a scalar. So pi acts by a scalar. It commutes with everything. It acts by a scalar on the center, on the representation. And so this will be our second invariant. And so the description of cohomological representations that I'm about to give, it'll be sort of a characterization in terms of the K types, not the K types in general, actually a specific K type. We'll see this a little later on. And the Casimir eigenvalues with the scalar pi c. Let's give an example. Okay, so if I have SL2R, then K is SO2R. And I can view K as the maximal compact, but I can also view it as a torus. I mean, it is also as a maximal torus in SL2R. And so the decomposition of, let's say for starters, the finite dimensional representation, E of SL2R into K types, is also the weight decomposition. I can sort of take the weight decomposition with respect to this torus. So here I've written down the 5-dimensional representation of SL2R. Each point is a copy of C as a representation of K. This is just sort of 5 one-dimensional subspaces, and each number under tells you the weight through which K, my torus, acts. And then to zoom this up to a representation of SL2R, I have lowering and raising operators that sort of move me from one weight space to another weight space. This is the 5-dimensional representation. Okay, so in general, if E is a D-dimensional representation of SL2R, it has extremal weights plus or minus D-1. So here it's the 5-dimensional representation, and I have extremal weights 4 and -4. And then the 2 representations of SL2R with cohomology in E are the 2 representations plus or minus. They're going to be the 2 discrete series that satisfy the following 2 things. Well, first we need that their Casimir eigenvalue has to be equal to the Casimir eigenvalue of the representation rho. And in this case, I'm just telling you the answer. The extremal K types are going to have to be plus or minus D+1. So they're going to be sort of, I mean, I'm going to show you the picture, right? So I have these K types. They're going to be sort of, one of the 2 representations is going to be a lowest weight representation whose lowest weight is d plus 1. So I'm going to call this pi plus, the holomorphic discrete series. The other one is going to have an extremal k-type, which is going to be minus d plus 1. So this will give me the anti-holomorphic discrete series. And so in here we see, and of course, this works with a 5-dimensional representation, but works in general for any finite dimensional representation. I get 2 discrete series that, if you will, hook up with my finite dimensional representation, in the sense that they have non-zero x with one another, because they have k-types that are adjacent to those of my finite dimensional representation. And so this is going to be the type of picture that we're going to want to generalize when we want to talk about cohomological representations. So cohomological representations are going to be determined by the right infinitesimal character, and also by k-types, which, so I've sort of said it, these derived functors, we can also think of them as x, of course, and so as sort of, let me just say that. Okay, so let's now move on to an actual theorem that characterizes these cohomological representations. So G will be a reductive Lie group with maximal compact K, Lie algebra G. C in the center of the universal enveloping algebra of G will be the Casimir. I'll have a Cartan decomposition, and then pi H will be a near-reducible unitary GK module, and rho E a finite dimensional representation of G. Well, a finite dimensional GK, whatever, they're the same for finite dimensional representations. Okay, so what does the theorem say? First, if the infinitesimal character of, if the Casimir eigenvalue of pi is not the same as the Casimir eigenvalue of rho, then there is no cohomology. So the cohomology vanishes. And so this already gives an immense restriction on which representations can have cohomology with coefficients in E. They have to have the same Casimir eigenvalue as rho. And then second, when the Casimir eigenvalues are equal, well, then the ith cohomology, this pi k here, it should be an h, I apologize. Well, it's equal on the nose to this apparently much easier space to compute, Hom k of k Homs, between the tensor product of E, which with the I exterior power of P, so this is a k representation, so the k Homs to H, so sort of the number, I mean, if you're just thinking about the dimension, is really the number of sort of shared k types. Okay, so the summary of this theorem, for which I'll sort of say a few words about the proof, is that the representation pi is cohomological if and only if it has the right Casimir eigenvalue and one of finitely many k types, right? So this is a finite dimensional representation, this is a finite dimensional representation. This, if I decompose semi-simply as a representation of k, and if I have one of these finitely many k types, then H will have cohomology. Okay. So let me say a bit about the proof. Oh, yeah, as an exercise. Okay, if you don't want to follow proofs and instead you just want to do some computations as you listen to me talk, for G, so okay, if I look at G SP4 of R and K is U2, sort of the compact form of the Siegel-Levy, you can try to compute all the k types appearing in pth exterior power, the ith exterior power, so we have P for I equals 1, 2, 3, and so that sort of, I don't know, it's a good, nice little practice for Thursday, and sort of nice little practice computing representations. Yeah, computing with the adjoint representation. It'll be a good warm-up for Thursday. For those who want to continue with the proof, let's continue with the proof. So the proof sketch will be the following. Okay, so this looks and will be like Hodge theory. And so what this is going to be sort of an algebraic string of argument that mimics a Hodge theory. So what we will want is an inner product so that we can talk about adjoints. Then we're going to have an adjoint delta, which will be a different delta later on. I see that I made a typo, to the differential. And from that, we'll make a Laplacian. And the representations that contribute to cohomology will be the representations sort of for which there are harmonic forms. We'll really get sort of that the forms on which the Laplacian trivially are going to be the ones that contribute to cohomology. And a key fact in this proof will be that the eigenvalue of the Laplacian is the difference of the infinitesimal characters. And so if this infinitesimal characters are equal, then all forms will be harmonic, in which case all forms will give us cohomology, so really just like in Hodge theory. Or if the eigenvalues are equal, then no forms will be harmonic and we'll have no cohomology. So that's roughly how the proof is going to go. Okay, the inner product. So this is what makes everything work. And the fact that there's an inner product just comes from the fact that everything in sight is equipped with an inner product. So pi h, whether it's the restriction or not of a unitary representation, it's sort of, I have the assumption that it's a unitary GK module. And what that means is it has a non-degenerate scalar product that is preserved by the action of the Lie algebra. Okay, also the second piece of data, the finite dimensional representation. Well, it's a finite dimensional representation. I can certainly equip it with an inner product, which is K invariant. And also I can make it so that the operators in P are self-adjoint. And then finally, P, well, is also equipped with an inner product with the killing form. And so what this means is sort of, since everything in sight is equipped with an inner product, I can have sort of my cochains. Okay, so this is not quite Hom K wedge Q of P, which is what we want. So the complex that computes cohomology. This is a slightly bigger complex. It's Hom C wedge Q of P, which I can write as sort of the dual of the qth exterior power of P, tensored with H, tensored with E. And this, well, the reason I'm working with this is because this is what is equipped with an inner product a priori. Inner product is great because then I can have, so I'm going to call this DQ, and soon we'll see that everything sort of is K equivariant, so I can pass down to CQ the K Homs here. Yeah, so the good thing is, since everything in sight is equipped with an inner product, then so does my complex. Okay, and if I have an inner product, I'm good because then I can speak of adjoints. So just notationally, I'm going to let tau be the representation, sort of pi times rho, sort of the representation acting on H tensor. Okay, so we had this map, which is a priori defined only at the differential, which is a priori only defined on or already defined on my space DQ, sort of C homomorphisms between the exterior power and H tensor E. So here it was in coordinates in all its glory. I'm showing it to you not because I'm going to use it in the proof, but just to sort of convince you that it's completely explicit. And what we're going to do is we're going to have sort of an adjoint operator delta that'll go from dq to dq plus 1. And the definition of this delta sort of, well, yeah, the definition of this delta is that you fix a basis of P, which I'll call yi, and then you just sort of define it as is. So sort of delta q plus 1 of the Q form phi is, there should be a Q plus 1 here. No, sorry. Yeah, okay. Is the sum, okay, I'm not going to read this formula, but the point is there's a very explicit. Then we get sort of by just manipulations and checking that delta is K invariant, that it preserves our smaller space CQ, right, consisting of K homomorphisms, the one that we want to use to compute the cohomology. And that it's adjoint to D, which is really what we want. Okay, and from this adjoint map, we can now define a Laplacian. And so as we do in normal Hodge theory, we'll define the Laplacian to be d delta plus delta d. it satisfies all the things that we normally want to satisfy. So Laplacian of phi paired with phi is d phi d phi plus delta phi delta phi. And that sort of buys us that, well, it vanishes. Sort of it kills phi if only phi is closed and co-closed, so killed by d and delta. And very importantly, so sort of this is what makes this whole thing work. And this is where sort of really the fact that we're working with Lie algebras that have a ton of structure appears, is that if I have a Q form, and I want to look at the eigenvalue of the Casimir operator on this Q form, or at the eigenvalue of delta in Q form, well, delta will act by the same scalars, or will act by scalars and by the same scalars as rho of C minus pi of C. And so this is sort of an important, I mean, it is the important input that makes the whole thing work. And I didn't, yeah, the proof is just sort of an explicit computation in coordinates. That's why I put the coordinates 2 slides ago, or last slide, to sort of just convince you that really what one needs to do is just, I mean, of course, the insight is sort of wonderful, but the proof is sort of a computation in coordinates. Okay, and so now we're in a good position. We want to prove 2 things, right? First, that if my coefficient system E and my unitary representation H have different Casimir eigenvalues, then there's no cohomology. And second, that if they have the same Casimir eigenvalues, actually the cohomology is just literally CQ. The complex is acyclic, if you will. So sort of all the differentials are 0, and the cohomology is literally Hom K of this. So let's see what we have. Well, again, we have our Laplacian. We know that phi is in the kernel, phi is harmonic if and only if it's closed and co-closed, and that the eigenvalue of the Laplacian is the same as the difference of the 2 Casimir eigenvalues for rho and pi, so for E and H. And okay, let's look at the proof of 1. Let's phi be a cocycle. And okay, so in this case, we assume that pi of C is not equal to rho of C. Okay, then D kills phi, and so delta phi is D delta phi. And we can just realize phi as delta phi divided by the scalar, whatever it is, it's 0, or it's D delta phi divided by the scalar, and this is visibly a coboundary. And so everything that's a cocycle is a coboundary, and so there's no cohomology. So again, this is very much like Hodge theory. Okay, and then for 2, then the assumption is that, right, from this equality, in the case where we have the same Casimir eigenvalue, the assumption is that everything is harmonic. And since everything is harmonic, well, everything is closed. And so all the differentials are 0. And then, well, if all the differentials are 0, then the cohomology is just computed by the actual dimensions. Okay, so I hope I've convinced you, even though I didn't write everything in coordinates, that what matters is for the representation pi to have the same Casimir eigenvalue as E, and that once we have that, all we need to do to compute cohomology is just to sort of find whether pi contains the same k-types as wedge I of p tensor dual. Okay, great. So what are these representations that have the same infinitesimal character as E, or the same Casimir eigenvalue as E? And the right k-types. Are they numerous, rare, hard to produce, mysterious, easy? And the good news is that they're very well studied. There's only finitely many of them for a given group G, and they're all explicitly constructed. And so that's what I'll talk about for the rest of the talk. I'm going to have a sip of water again. If anyone has a question, happy to take it. Okay, So for this third part of the talk, give an explicit description of cohomological representations. So the theorem that we'll talk about is the theorem of Vogel-Zuckerman, which answers our previous question. So suppose that rho E is an irreducible finite dimensional representation, and that of G, and that delta, okay, here I'm using their notation, that delta is an irreducible representation of K hat that occurs in the space, right? So this is E dual tensor with, oh boy, okay, E dual tensored with wedge I of P, let's say. So Hom C E of wedge I of P, then there is at most, they show that there is at most one unitary representation with the following properties. Well, it has the right infinitesimal character, and it has the right K-type. And this, so far, we knew that the infinitesimal character and the K-type were enough to characterize the representation, but there could have been a whole slew of inequivalent representations that have the right infinitesimal character and K-type. And what the theorem of Vogel and Zuckerman tells us is no, actually, once you've pinned down the infinitesimal character and you've pinned down a K-type, that's it. You've entirely characterized the representation. And then they also tell you, if pi exists, then there's a whole bunch of things that you can explicitly compute just from this K-type delta. Okay, well, the entire cohomology. Also, the realization of pi as a Langlands quotient, so sort of how pi fits in the classification of the Langlands classification of representations of your Lie group G. And you can actually access the entire string of K-types that appear just from knowing this one K-type and this infinitesimal character, this Casimir eigenvalue. And so this is very powerful. It says that as soon as you know this, you know essentially everything you want to know about this representation. Okay, so again, the upshot and the important for us upshot of this theorem is, since there's finitely many K-types in the Hom E wedge I of P, then there's finitely many cohomological representations with coefficients in E. These cohomological representations, they've been constructed. So at the time of this Vogel-Zuckerman theorem, they're already constructed by Parthasarathi, by Zuckerman, and by Speyer-Vogel. I'll talk about the first two constructions very rapidly towards the end of the talk. They're built from combinatorial Lie algebra, more than combinatorial, Lie algebraic data called theta-stable parabolic subalgebras. And these theta-stable parabolic subalgebras, they're built basically by some sort of version of parabolic induction, in which instead of taking a parabolic that's defined over R, you take a parabolic that's defined over C and not over R, but whose Levy subgroup is defined over R. So that's sort of the main piece of data that goes into the construction of these representations. Okay, so let me tell you a little bit about these theta-stable parabolic subalgebras. So I have G, this complex Lie algebra, but I'll have G naught, that'll be the real algebra of G. And in general, if I put a subscript 0, that'll just mean the real, sort of a real object of which the non-subscript is its complexification. And recall we have this Cartan involution that splits the Lie algebra of G into the compact part and then the tangent space of the symmetric space. And this is the theta. This is the theta in theta stable. So it's the Cartan involution. And I'm going to assume just now, just sort of for exposition, it's absolutely not necessary in the theorem, that I'm in a situation where the rank of K is the same as the rank of G. So this will be the case for SL2, will be the case for SP4, but of course it's not. There's many Lie groups that are reductive groups, which is very interesting, in which it is not the case. It just makes things easy for me. Okay, so how does one produce theta-stable parabolic subalgebras? So what are they? Well, to make them, you take an element, so in the maximal Cartan, the Cartan subalgebra contained in K, and the real parts of it in I times the real parts of it. So you rig an element in your specific torus so that the adjoint so that as an operator through the adjoint representation, it will have real eigenvalues. So that's what you do, right? An element in K will have imaginary eigenvalues under the adjoint rep. And then if you put an I here, suddenly it'll have real eigenvalues. And you define this theta stable parabolic subalgebra Q. So it's parabolic. It has a Levy part and I don't know what to say, sort of a unipotent part. L is just the centralizer of X. So it's the sum of the 0 eigenspaces of ad X. And then U will be the sum of the positive eigenspaces of ad X. And this gives you a parabolic subalgebra. And since X, it started in K, so it's fixed by theta, well, then Q is also fixed by theta. So it's theta stable. Moreover, if instead of taking Q, I take Q conjugate, then the I becomes a minus I, and I just get the opposite parabolic. The positive eigenspaces become the negative eigenspaces. And finally, importantly, our Levy part of the subalgebra, the whole thing is defined over C, right? It's not fixed by conjugation. But the Levy, well, which is the intersection of Q bar and Q, sort of Q opposite and Q, that's defined over R. So the Levy is the complexification of sort of real the algebra of a Levy defined over. So that's what these theta stable parabolic subalgebras are. I've told you how you produce them. That's not the same as classifying them, but it's a start. Okay, let's look at SL2. It's the Lie algebra of SL2 is traceless matrices. The Cartan involution sort of in these coordinates is negative transpose. Then I have my maximal compact K, which is in fact already a torus, a one-dimensional abelian Lie algebra T, and then I have a two-dimensional P. Okay, and then in this case, for SL2, there are 3 conjugacy classes of theta stable parabolics. Well, I can take the element 0, 0, 0, 0, which is the origin. I mean, in that case, well, if I take the centralizer, it's the whole thing. So in this case, Q is the same as L, it's the same as G. Or I can take, for example, this non-trivial element. So I'm going to give you 3 representatives from these 3 conjugacy classes. I take 0, I, negative I, 0. Then I'll get Q plus, this theta stable parabolic algebra that I call Q plus, in which case, for which L is T is K, so sort of the centralizer is just this span of X. And then U is the one-dimensional subspace spanned by this matrix. And if instead I take the conjugate over GL2, but not conjugate over SL2 element X, then I get Q minus, in which has the same Levy, but of course is the opposite algebra. So here, if you look, all I've done is sort of taken the complex conjugate. Okay, so these are what these theta stable parabolic subalgebras are. From now on, just for simplicity, I'm going to assume that my coefficient system is the trivial coefficient system. Again, it's just for simplicity. Okay, then given a theta stable parabolic subalgebra, one can construct from it an irreducible GK module called AQ. That's how we call them. For SL2, okay, for SL2, let's go back to our example. Well, if Q is the full Lie algebra, then AQ is the trivial representation. So the only finite dimensional representation with cohomology. Then if Q is Q plus, then AQ is going to be our holomorphic discrete series pi plus. And if Q is Q minus, AQ is going to be the anti-holomorphic discrete series pi minus. And so from these 3 theta stable parabolic subalgebras, I've sort of reduced the trivial representation and the 2 discrete series representation, which I sort of told you before, and you were also told last week, were the representations with cohomology. Okay, let me give you some properties of the representations AQ. So if you fix a set of positive roots of K with respect to the torus T, so that it contains the roots that are both in U and in K, sort of, you have to fix a set of positive roots. This prescription that it contains these roots, it doesn't necessarily completely fix the set of positive roots. So there's a choice to be made. Once you've made this choice, AQ restricted to K, so this sort of semi-simple representation, it contains the irreducible representation with highest weight to row of U. So sort of, again, if you have some positive roots, you can sort of look at the roots of K inside of the intersection of U and P, take all the positive ones and take the sum of, this is just the sum of all the roots in this space. Okay, so this is a K representation with a certain highest weight. And the representation at AQ, also we know that the center of, or it's proved that the center of the universal enveloping algebra acts on AQ by the same scalars as on the trivial representation. And so these two pieces of data will be sufficient to tell us that AQ is cohomological. So this, the representation with this highest weight, well, you can see there's a P here, so it's completely believable that it looks like a piece of the representation of K on P, or the representation of K on an exterior power of P. And it is the case. So the representation AQ, it has these two necessary pieces of data to tell us that it's cohomological. Okay, a few words on the construction of AQ. So I'll tell you a bit about Partha-Sarathy's construction. So Enright and van der Arajan, they constructed, they answered a question, which is, what are the GK modules of the discrete series representation? And they did this by sort of explicitly constructing the underlying GK modules of the discrete series representations, so sort of specifying the weights, most importantly, the K weights. And in Partha-Sarathy's article, he's trying to extend this, sort of extend their construction to a larger classes of representations. And by so doing, he constructs all the AQs. And the AQs are realized as suitable quotients of completions of a certain Verma module for K. So you start with the Verma module for K. From it, you produce a chain of GK modules for Q, which are not necessarily irreducible, but by taking suitable quotients of them, you produce irreducible representations, which will be the AQ. And really, I wanted to sort of justify in this case why we start from these theta-stable parabolic subalgebras. And the key property of a theta-stable parabolic subalgebra in this context is that it's a parabolic subalgebra of G, such that if you intersect with K, you also you still have a parabolic subalgebra of K. So sort of that's the key point that makes this work. I mean, there's a lot of work that goes into it. And the construction is completely explicit. And so you really have sort of the list of weights of this construction. Okay, and then the second construction by Zuckerman is more geometric, or sort of aims to give a Lie theoretic analog of a geometric construction. So it relies on the Zuckerman functors. And it realizes AQ in an algebraic version of Dolbeault cohomology. So sort of it realizes the representations AQ in certain cohomology groups associated to the Zuckerman functors. So what are the Zuckerman functors? Again, I won't be extremely precise. But here, the fact that Q is theta stable buys you a completely different a priori fact, which is that the quotient G mod L, sort of, we had this Lie group L, which was for which sort of frac L was its Lie algebra. This quotient has a complex structure. It's not just, it has a complex structure. And then what Zuckerman does is he constructs an algebraic analog of Dolbeault cohomology. So sort of in the same way that maybe we had an algebraic, well, not in the same way, but a prototype for it could be how we had an algebraic analog of Hodge theory earlier. And then the AQ appear inside the derived functors of taking certain sections of certain line bundles on G mod L. Sort of, there's a whole, sort of, he defines these Zuckerman functors. So those are the constructions. We have at least two. There's this third construction of Schmee-Voggen, which I won't talk about. And then in the Voggen-Zuckerman article, they show that these representations AQ have cohomology, and that any representation that has cohomology will be isomorphic to one of these AQs. Okay, how do they compute the cohomology? Well, since AQ has the same infinitesimal character of the trivial, it's just the cohomology, the GK cohomology of AQ is just this Hom space. We're going to let R be the dimension of U intersected with P, so sort of the part of the unipotent part of early algebra intersected with the symmetric space. And then Vogt and Zuckerman do the following reduction, where they show that this a priori K-Hom between wedge I of P and AQ is actually equal to the space of K intersected with L's Hom of, okay, so what's happened? Still an exterior power. Instead of the ith exterior power, it's the I minus rth exterior power. So I've sort of corrected it by this dimension. And now instead of having P, I don't have all of P. I just have L intersected with P so that it can be an L representation. And what I win by this, well, first, taking smaller exterior powers, but also I've changed my coefficient system from AQ, or really from this specific weight of AQ that I was talking to you about before, to C. And now this is a very sort of straightforward computation. You're just looking for copies of the trivial inside this bit of the exterior power of the adjoint representation. Okay, and one thing to observe is that AQ is going to contribute to cohomology in a range of degrees that's sort of centered around dim P over 2. So, right, this will certainly be non-zero. We'll certainly have cohomology when I is equal to R. And these representations, I haven't said it, I can't remember if I could say it, but they satisfy Poincaré duality. So we'll also have it dim P minus R. And then there might be cohomology in intermediate degrees if the trivial representation appears in these intermediate degrees. Okay, so I'm arriving at the end of my talk. So again, we have these AQs. They're the only representations with cohomology. They have an explicit construction, and once you have your hands on one of them, it's a very explicit calculation to actually look at the cohomology. Again, that's what we'll do for SP4 on Thursday. And an important thing going on here, just to sort of tease the rest of the talks in this section, is, as I just said, you're going to get cohomology. I mean, except if R is dim P over 2, you'll get cohomology in several degrees. So in a range of degrees in, for example, R and in dim P minus R, and they'll all come from the same representation, AQ. For SP4 on Thursday, we'll see that some representations contribute to both H2 and H4. And okay, there's a global picture, which I hope has been sort of talked about in the other talks. In the Langlands program, where an automorphic representation, well, it has a representation at infinity, which is a lot what we've been talking about today, but also representations at the finite places. And the corresponding cohomology classes in the cohomology of arithmetic groups, they'll appear in different degrees in cohomology, but they will correspond to the same finite factors as automorphic representations. And so a way to say that is that they'll have the same Hecke eigenvalues. They'll have the same Satake param. And so this observation that the same degrees of cohomology show up, so the same Hecke eigenvalues show up in different degrees of cohomology. And the idea that this should be explained not by the usual Hecke operators that act on only one degree of cohomology, but on derived Hecke operators that shift the degrees of cohomology. So that's the starting point for the Prasanna-Venkatesh conjectures, which I believe are sort of the end goal of this specific sub-series of talks. Okay, thank you.
Yeah, let's thank our speaker. Right, so does anyone have any questions? Yeah, feel free to unmute and ask if you do.
I'm following up on my presenter, the last week's presenter, and I also have all my references, which I thought was a wonderful thing to do. So you want to see?
Um, yeah, I don't know. I guess I can ask something if no one's asking anything right now. Do you have any idea where the idea to motivate, like to do something analogous to Hodge theory came from?
Has to be compact groups, right? Uh,
Okay.
my guess is they were. I mean, I think maybe they even say that in a.
Okay.
Uh, uh, yeah, you like if
So
you want to
sorry.
compute the cohomology of a certain compact group, just as a sort of as a manifold, you can do that using the Lie algebra. My guess is how this started. I want to
Hmm.
say with Cartan,
Sorry.
but oh
Could I ask what was the question?
yeah. Oh, what was the question? Rahul,
Yeah.
you want to ask the question? Maybe you know better than I. Hi.
Sorry, I arrived a bit late, so
It's
I
okay. I'm very
Yeah,
happy
the
to.
yeah.
question is
Anyway,
where the
nice.
idea to like this first proof of the first result in the talk. Sorry, I'm just forgetting the two names. It was Burrell and someone else.
Yeah, it was Burrell. I mean, I read it in the Burrell Wallach book. Maybe it was proven by
Yeah.
someone else.
Burrell. Okay.
Oh, the idea to use Hodge theory. I think Matsushima was the first to do that actually.
Uh-huh.
Like way back in late 50s or early 60s. So he
Uh-huh.
had a series of papers where he basically tried to work out Hodge theory for compact. In the case of compact quotients for the invariant metric, what does, Hodge's theory tell you?
Uh-huh.
And he sort of, I think he had a series of papers where essentially culminating in what we now call Matsushima's formula. But first, I think he worked for like in the Hilbert modular case or, things like that.
Uh-huh.
I mean, I looked at these once a long time ago. They're, of course, very messy to read because a lot of explicit things are going on. But yeah, but I think maybe he was the first person to think that you should try to make Hodge theory completely explicit for G mod, K mod, gammas, which are compact.
Uh-huh. Uh-huh.
Yeah. Of course, Cougar had something to do with it also, right? Because he proved this formula around the same time. But
Yeah.
but I don't know exactly where that came about. Um, right. Thanks for a really nice talk, I should say.
Oh,
Yeah, I mean,
Yeah, that's
yeah,
fun.
it was nice.
Yeah.
Hello, Rahul. How
thanks.
are you?
Good. How are you?
Good to
Yeah,
see you. Good
there's
to see you.
another sort of crazy part in the talk where like the sort of key calculation that the Casimir acts by like rho of
Yeah.
E with rho of pi
Yeah.
that
Yeah,
was the explicit calculation and it's sort of a miracle the way it's there,
Well,
right?
when I
it's
was
very
preparing
nice. Yeah,
when I was
yeah.
preparing the talk, I like looked at it for a while and I tried to sort of extract understanding out of it. I was not able to. Like it was just some sort of miracle that was like there's many like commutators that just commute to the right thing.
Yeah. So, I mean, I think if I remember correctly, you choose a basis which is well adapted to the killing form, and then, but at some point, just something so silly as the structure constants of the Lie algebra having some symmetry kind
Yeah.
of makes it work out. Yeah,
Yeah.
it's quite
The
cute.
Yeah.
calculation of the structure constants coming in. Oh my God. Okay.
Yeah, no, but no, it's only like half a page actually. So
Yeah.
I
Wow.
would
Yeah.
recommend. So I think that appeared in a paper of Matsushima and Murakami. So I'm still not sure why. But Kuga obviously knew this, so maybe if Kuga wrote about it, I don't know. Um, but yeah, anyway, it's a nice calculation. I mean, it's simple but nice. Yeah. So
Yeah, someone must have some intuition for like why you would even expect something like that to work, but
Yeah.
I guess that's part of the Hodge theory thing. So
yeah, it's right. Yeah, no, I mean, I think I went through this. I mean, I think I wrote. I mean, I gave a talk about some school. I mean, a very basic level school where I wrote some notes. And it's fun to do this calculation, actually. It's kind of clean, nice. But it's not the sort of thing you do at the board, of course. So,
yeah.
yeah. Yeah. Well, Um, great. I just wanted to remark about the last thing you said.
Yeah.
As far as I know, like, so for example, for this SP4 thing, the
Mhm.
fact that like, if you take essentially any, okay, so take the one of the AQ lambdas, which is not discrete series and not the
Mhm.
trivial. So
Mhm.
then you get cohomology in degrees 2 and 4, right?
Mhm.
That is true for, Yeah, that's true for both of the GK, both of cohomology. Yeah, okay. So it's actually interesting that at the moment, I don't think this quite fits into, meaning the Venkatesh and Prasanna Venkatesh formalism has not been extended to non-tempered situations, the conjectural formalism. So in fact, you see, there you'd be looking at global automorphic form whose infinity component is non-tempered. And okay, so let's assume that you had a globally non-tempered thing. So then actually their conjecture doesn't yet apply. There's something interesting. So I would say that the fact that you have the same Hecker eigenvalues appearing in degree 2 and 4, although it should be explained by the same sort of mechanism, there isn't an explicit conjecture there, I think. But anyway, yeah.
Yeah.
But
So I guess it's in the
question.
it's in the non-discrete series. Well,
no, the non-tempered case.
Yeah, exactly. But
yeah. So the
yeah.
non-tempered, non-trivial. Okay, so the other extreme for the trivial case, Akshay's paper kind of covers what has to be done, right? So yeah. Anyway, that's, I mean, it's an interesting case where it would be interesting to see that mechanism in play somehow. But anyway, yeah. So it's like one more thing, actually. Okay, so now I'm old enough to start making like historical comments. So
yes, but I want to hear them.
Yes,
no. Sorry, no. So this is very interesting. Something that I learned only. So there was this conference in October in Allahabad at the Harish-Chandra Research Institute for the centenary of Harish-Chandra, right? And of course, Parsati was there. And Parsati made a really interesting comment, which he said that, like, so, how he started looking at constructing these AQ lambdas, right? The AQ lambdas for Q, not a Borel, right? So he was, of course, in print, he explicitly says that, he was inspired by the Varadarajan and Enright Varadarajan paper where they constructed the algebraic discrete series. But then he said, I never thought about it before, but I had a conversation. So he was at the institute as a postdoc in 1972, and he had a conversation with Langlands about Langlands' multiplicity formula. So, Langlands had a conjectural formula for, well, you guys know, as I said, better than anybody else, but anyway, for the dimension of space of automorphic forms which are cuspidal and therefore, or tempered. So the infinity component discrete series, right? I'm talking about his conjecture, and I think maybe the Boulder conference in the 60s or something like that. So so Parsati had thought about, maybe one should try to extend this to other pieces of cohomology of G mod, K mod, gamma. And so he told me he was under the impression that, he thought there would be kind of no other interesting representations, for example, with H1. I mean, I don't know how seriously he thought that. And he said he had a conversation with Langlands, and Langlands told him, no, there are lots of representations. And he told him about a paper of Hirai about O1N. I don't know if you guys know this paper. I think I've never looked at it, but I think it's an important paper, but I've never really looked at it. So by this Japanese mathematician Hirai, and Hirai constructed some representations of SO1N. And so then Parsati said, so he looked at that paper and then he forgot about it. But now looking back all these years later, he thinks he was actually partly inspired by that paper. So, but I mean, yeah, so he mentioned this in October and he said, I never thought about it before, but now it occurs to me that I must have been slightly inspired by that. Anyway, so yeah, so it's kind of interesting, this thing, because I think in his paper which you mentioned, where he constructs the AQ lambdas, he just sort of says, generalizing and right Varadarajan, these are some interesting modules. Yeah. He also gave some talks about 10 years ago in TIFR about his construction. Yeah, I have to say, I can't say I got anything out of that. But anyway, so it's sort of very, it's unclear what's going on, right? Somehow, yeah. That's elementary. Anyway, so that's, yeah. Anyway, so I just wanted to ask, I think Devendra had mentioned you might give a third talk in your series now, or you might give talks later. Is that decided?
I don't know, Devendra, is it decided?
Yeah, it will be decided after Karthik speaks.
Okay, fine, right. Great. Okay, so
at that point we will judge what will be the topic of the talk, maybe.
Okay. Yeah. Okay. So I was hoping to give some talks that would help the audience and myself sort of understand better what Karthik will talk about.
Right. No, so sounds good. Yeah, I mean, I guess So are you going to talk about limits of discrete series also in the, I guess you won't have time. So in the one more talk, right?
Yeah, I'm not sure. I was rereading their paper this morning and I thought, oh, maybe I should, but let's see what I can prepare in 2 days for Thursday.
Okay, great.
But certainly certainly, for example, if Kartik says what he would like other people before him to talk about,
So yeah,
I'll be happy to sort of oblige.
Okay, great.
Yeah. Will you give a talk in this series?
I guess I'm not sure. So I mean, in the sense that I'm supposed to be giving, but I don't know what. I'm not quite sure. Yeah, right. So I have to say that I've been really haven't given it any thought, but I'm not sure what I would talk about also. So let me see. So as I understand, Devendra, Karthik is speaking in June, right?
Yeah, 11 June and maybe 10 June also.
Okay. Right. Yeah, I don't know. Maybe. Yeah. Okay. Maybe I should
And then later
think
also,
about.
like maybe July, August.
Okay. Okay. Great. Rahul, you're giving some talks later, right?
Yeah, I think the
Last
end of
week of
June.
June.
Sorry?
Last week of June.
Last week of June. Okay. Great. Okay.
Trace formula.
Yeah. We'll see how much I can say.
Right. Great.
It'll probably just be like a big overview because there are too many details to get into. But
Sure. Yeah. Great.
Yeah. Oh, this was fun. Yeah, I've never seen that before. I should have. That was really cool.
So actually, I have a short note on like Matsushima's formulas, which maybe, I mean, it's not a published thing. It's just some notes. Maybe I'll send it to you, Rahul, because I abstracted what's necessary for the calculation about Kugat's formula and all from that. But
Okay.
I can send it to you guys. I
Yes,
mean, there's nothing in it. And also, actually, it was meant for this school, as I said, a long time ago. And mainly, there are some toy examples discussed, which, but it's very elementary stuff. And you guys, of course, are much more know this stuff pretty well already.
Well,
we do calculations in the privacy of our own home.
That's right.
Yeah.
Like
also, yeah, elementary doesn't mean easy, right? Because
exactly.
Yeah, you need a lot more intuition that's sort of harder to develop to like go on the right path sometimes.
Yeah, that's true. That's true. Yeah. So I mean, yeah, and it's okay. So I'll send it to you guys. I mean, it's just some random thing that a few pages of notes. But for example, I dug up this calculation and tried to clean it up as best I could. Although not that I have, but somehow. So yeah. Anyway, okay, great.
Yes, thank you. This will be fun. Yeah.
Okay, great. Thanks.
Thank you.
Thank you.
See you next Saturday, Thursday.
Thursday. Yeah, sorry about this timing because the time is a bit odd. I missed like the beginning. I realized. Yeah. Okay.
Yeah.
Great. See you guys.
Okay.
Sorry. Okay. Yeah.
Thanks, Rahul.
Thanks, Rahul, for chairing the session.
Oh yeah.
See you on Thursday on the same time. See you on Thursday.
See you on Thursday.